We need a super battery. And where the super battery going to come from? We think from quantum computers. Batteries, there's no digitization of a battery. It's a chemical reaction.
What if the next battery could charge in a blink, without chemicals, without smoke, just pure physics? Energy storage already runs our lives, and we will need far more as demand rises, while wind and solar swing up and down. Today, we are diving into quantum batteries, a real research idea that sounds like science fiction. These devices are still tiny lab demos, and much of the work is theoretical and debated. But the science is fascinating. It shows how atoms store energy in steps, and why that matters. By the end, you will see fire, lasers, and sunlight differently. What quantum really means. The word quantum is often thrown around like a buzzword, but it has a clean meaning. Quantum describes the smallest possible discrete unit of a physical property, such as energy or matter. Discrete means it comes in steps, not in a smooth slide. At our scale, those steps blur together, so things look continuous, but inside atoms, the steps become obvious. To explain quantum batteries, it helps to picture a single atom. The most accurate picture is the Schrödinger cloud model, but the Bohr model is clearer for this story. In Bohr's model, electrons sit in rings around the nucleus. When an electron jumps from an inner ring to an outer ring, the energy of the atom increases. That jump, that stored increase, is the foundation we care about. If we only focus on energy, we can simplify even more. Imagine a ladder. Each rung is an allowed energy state. The atom can be on rung 1, rung 2, rung 3, and so on. Charging a quantum battery means pushing electrons up to higher rungs and keeping them there. Discharging means letting them come back down and using the released energy. In this step-like world, in between is not allowed. An electron cannot rest halfway up the ladder. In solids, many levels blend into two main bands, the valence band and the conduction band, but the step logic still matters. Why storage keeps getting harder? Energy storage is everywhere. It is in your phone, your laptop, and the backup unit that keeps a home running when the grid goes down. It is also in power plants, where stored energy smooths out peaks in demand. We will need more storage for one simple reason. Electricity use keeps climbing, while many clean sources are variable. Solar fades at sunset. Wind can drop in minutes. Even hydro and gas plants have limits on how fast they can respond and how long they can run. Batteries, pumped storage, and other methods help, but none is perfect. Materials are limited. Costs matter. Space matters. Losses add up. That is why researchers keep hunting for breakthroughs, even ones that sound strange at first. Quantum batteries fit right into that pattern. They are not a magic fix, and they are not close to powering vehicles or phones. They have only been tested at an incredibly small scale. Still, the ideas behind them are worth learning, because they offer a new way to think about what it means to charge something in the first place. That is why grids also use pumped hydro, compressed air, heat storage, and hydrogen. Each option has limits in cost, place, or loss. So new ideas keep showing up, even if they start as lab curiosities. The everyday proof hiding in a flame. Now for the fun part. This is not only a lab thing. You have seen electron jumps your whole life. Flames glow because heat pushes electrons up, and then they fall back down. In a flame, atoms and molecules get energy from heat. That energy can lift electrons to higher states, but those higher states are unstable. The electron does not want to stay up there. When it drops back down, the atom releases the extra energy as a photon. That photon is light, and that is why fire shines. The color of the light depends on the gap between energy states. Bigger gaps produce higher energy photons, which means shorter wavelengths. Smaller gaps produce lower energy photons, which means longer wavelengths. That is why different elements can make different flame colors. It is also why some materials absorb some wavelengths of light, but ignore others. If the incoming light does not match an allowed jump, it will not be absorbed. It is not almost absorbed, it is rejected. This is the weird beauty of quantum rules, and this rule matters for quantum batteries because it helps define how charging can be controlled. You tune the laser to the right wavelength, and you can pump energy into the system. Tune it wrong, and you get nothing. This is also why different elements make different flame colors. Different gaps mean different photon colors, and if incoming light does not match a gap, it is not absorbed, so it simply passes through the material. Charging with a photon and a laser. So how do you push an electron up the ladder? There are multiple ways, but the main method used in many quantum battery ideas is light. Light comes in photons, which are packets of energy. If a photon hits an atom and its energy matches the gap between two allowed levels, the atom can absorb the photon and the electron jumps up. In that moment, the system has stored energy. If the light does not match the gap, it will not be absorbed. The photon just passes through. That simple rule is powerful because it makes charging selective. You cannot charge by accident with any random light. You need the right wavelength, the right color for the job. In a study by James Quash and his colleagues, a quantum battery was built around a semiconductor placed in a microcavity. That cavity sits between two highly reflective surfaces that guide and trap light. The basic idea is to keep photons interacting with the material in a controlled way, so electrons can be pushed into higher energy states more reliably. In solids, energy levels smear into bands, but you can still think in terms of jumps between useful states. The experiment is tiny, but it shows the principle. It proves that you can charge a quantum system by driving it with light. In Quash's setup, the semiconductor sits in a microcavity between highly reflective surfaces. The cavity guides light so photons interact strongly and cleanly. That makes charging easier to measure, even at a tiny scale. The biggest challenge: stopping self-discharge. At this point, you might think a quantum battery is simple. Shine a laser, push electrons up, done. But there is an inconvenient fact. Electrons will jump back down if they get the chance. They will seek the lowest energy state they can reach. In normal materials, this relaxation can be extremely fast. That means the battery would discharge itself almost instantly. So the big question becomes, what stops it from leaking? One proposed answer is a dark state. The name comes from the fact that the atom can no longer emit or absorb a photon in the usual way. If it cannot emit, it cannot easily dump energy as light. That could hold the charge. But dark states are not easy to create, and the practicality of using them in real devices is hotly contested. Still, researchers explore ways to make it work. When an electron is excited in a solid, it can create an electron and a hole pair. The electron wants to recombine with the hole because that lowers the energy. But quantum properties can change the rules. One common property used here is spin. If the spin configuration makes recombination forbidden, the transition becomes slow. This idea is often described as spin-forbidden transitions. Magnetic fields can help control spin, but turning this into a robust battery is a massive challenge. It is a battle against noise, heat, and imperfections. Keeping a charged state is the hardest part. The dark state idea is promising, but creating it is difficult, and scientists argue about how practical it will be outside labs. Spin control with magnetic fields is one route. Getting useful energy back out. Even if you can charge a quantum battery and keep it from discharging, you still need to use it on demand. That means you must take the system out of the dark state and extract the stored energy in a useful form. If the energy comes out as a photon, you may just get light. Light is energy, yes, but it is not always the kind of output you want. Most devices want electricity moving through a circuit, so a key open problem is conversion. How do you take that stored quantum energy and turn it into a steady electrical current? One thought is to blend quantum battery ideas with solar panel technology. Solar cells already take excited electrons and separate charges to create a voltage and a current. If a quantum battery could store excited states and then release them into a circuit, it could act like a storage layer built into a light harvesting system. This is why some scientists talk about quantum batteries in the context of solar energy. The dream is not just to capture sunlight, but to store part of it immediately, without sending it through a large external battery bank. Scientists from the University of Adelaide have discussed how these ideas could apply to solar, where light is simultaneously harvested and stored. It is early work and it is still debated, but it shows why people are excited. It is not only about a new gadget. It is about merging the steps of energy capture and storage into one process. Even if the energy leaves as light, you could convert that light the way a solar cell does, turning photons into current. Researchers at the University of Adelaide discuss solar ideas that harvest and store light together. Quantum batteries will not replace your phone battery next year, and they might never reach that scale. Still, the idea is a useful mirror. It shows that energy can live in tiny steps inside matter, and that light can move those steps with perfect precision. It also shows why storage is hard. Nature loves to relax and waste nothing. Researchers in places like the University of Adelaide even imagine solar systems that harvest and store light at the same time. If you learned something, leave a like and share this with a friend who loves weird science. Now tell me, do you think quantum batteries will ever leave the lab?